Hi guys. About 2 weeks ago, we have talked about addition reasoning, right? So we talked about different strategies that students are doing or invented their own strategy to solve addition or subtractions, right? Uh, I'm gonna show you some models to solve multiplication, and also I'm gonna show you some examples of students' invented strategies to solve multiplication. While I'm presenting the multiplication reasoning, I want you to keep thinking about how each of these models, how each of the model is connected with each other. Okay, so keep thinking about that. All right, keeping that in mind, let's think about multiplication. So when we are introducing multiplication to young students, like second grade, from second grade, the students start the multiplication. Because they have the knowledge about addition, we start from multiplication as repeated addition model, right? So like 8 plus 8 plus 8, we have 8 3 times, right? So we add 8 repeatedly 3 times. That is the same as 3 times 8, right? We read this as 3 times 8. That is multiplication in the meaning of repeated addition. Sometimes we can read this as 8 multiplied by 3 too, right? Okay. So we know that 3 and 8 are factors and 24 is the product. So these names for each number, I think it's also very important. So one of the standard for Common Core practice standards, I think that's the sixth one, precision. It's about precision. So precise terminology is very important. For example, when we had two number addition, so 5 plus 3 is equal to 8. 5 and 3 are add-ins, and 8 is the sum, right? In subtraction, if we have 8 minus 3 equals 5, 8 is minuend, minus 3 is subtrahend, and equals 5, that 5 is the difference. In multiplication, we have 3 times 8 equals 24. We call 3 and 8 as factors, and 24 is the product, right? Some mathematicians are arguing about multiplier and multiplicand. I don't want to argue about that because everybody's saying differently, and it is not very important because 3 times 8 is equal to 8 times 3. It doesn't matter which one comes first and which one comes next, right? So just like when we add two numbers together, 3 plus 8, in addition, we call both 3 and 8 as add-ins. Similarly, we're just gonna call 3 and 8 in multiplication as factors. Okay, so the order doesn't matter. And we call that, final answer as product in multiplication. If we extend this notation, terminology to division, we know 24 divided by 3 equals 8, right? So we call 24 as dividend because that is the number that is divided, and divided by 3. So 3 is dividing 24, right? So we call that 3 as the divisor. So here in subtraction or division, the order matters. So we need to distinguish the terminologies there, right? And the answer equals 8 in that division. We call the answer of division as a quotient. If there's any number remaining, we call that as remainder. I just wanted to mention the precision of the terminology. And even when students are very, very young, I think it is important for the teachers introduce that precise terminologies to the students. One time I remember I observed one, I think it was third grade classroom. I was so surprised because even all third grade students in that specific class were able to use that right terminology for addends, factors, difference, all those names. Instead of they saying, oh, the first number or second number, they were saying, minuend, subtrahend in subtraction. So, wow, that is very, very important and that's very powerful. And the students felt so proud of themselves too. So that was very good practice for the teachers to use specific, terminologies. Even upper grade, like fourth and fifth grade students, and even high school students, when they're looking at the fractions, they say, oh, number above the bar or number at the bottom. That doesn't sound very precise, right? We want to say numerator or denominator for the names instead of the top number or bottom number, things like that, right? So we can help our students to be more matured by using exact terminology and mathematical terms. Okay. Okay, that was one thing that I wanted to talk about. And let's go back to the multiplication models. So the first thing we can think about is repeated addition models. And you can show repeated addition can be written as multiplication like that. So if you use a number line like that, for example, 4 times 5 or 5 times 4, we can add 4 5 times. So you can keep adding 4 each time, right? So if you have only one 4, you can jump to 4 from 0. If you have another 4, you land on 8. So we can say that, oh, it's 2 times 4. If we have 3 of them, it's 2 times 3 because it's same as 4 plus 4 plus 4. You can do the same thing for another 4 and another 4. So you can show the students 4 plus 4 plus 4 plus 4 plus 4. 4 is added repeatedly 5 times. So we can write this as 4 times 5 or 5 times 4, right? Okay, so that's the repeated addition model. We can also do use equal groups model. We actually do this a lot of times too because we can easily model with actual objects like M&Ms or cookies, teddy bears, something like that, right? You can just use whatever you have in your classroom. So that's very easy, and we can show, for example, you have 3 groups, and in each group, you're going to have equal amount. That is the key here, right? So you have 4 x's in each of this group. And you can ask how many x's are there as the total, right? So here in the units, we can say 3 groups. It can be a plate if it has cookies on the plate. You can say 3 bags if you put anything in a bag, right? In like 3 bags. These are the items in the bag or on the plate. And the answer should be exactly same unit as the objects in each group, right? Okay. So we can think about multiplication, about coordinating numbers and sizes of equal groups. So we can think about the units here. How many groups of what? The object is equal to how many of that object. So we can think about the units. The units are in each group equally, and the total answer should be that object. Okay? For example, if we have 3 plates of cookies and on each plate we have 5 cookies, we can ask using this, How many groups? How many plates? 3 groups or 3 plates of what? Cookies. How many cookies are on each plate? 5. So we can say 3 plates of 5 cookies is equal to how many cookies, right? So the units here and there is exactly the same. So you can add 5 plus 5 plus 5. So you can connect this to the added, repeated addition there, right? So we get 15 cookies. Another model is rectangular array model. We do this a lot of times too, right? So we can make arrays like that in a straight rows, and we count how many are in each row and how many rows there are. So in each row we have 4 axes, and how many rows are there? 3. So we can multiply that by 3 times 4. That's exactly same as I have 3 groups, and in each group I have 4 items equally, 4 axes equally. How many axes are there in total? 12, right? So you can connect that too. So another example here, how many cans? The cans are viewed from above, like bird's eye view, are shown here. So students can count this as how many rows are there and how many cans are in each row. So they can see, oh, I have 4 rows, and in each row there are 6. So 6 times 4 or 4 times 6, right? They can do 4 times 6, or they can do 6 plus 6 plus 6 plus 6 and get 24 there. Or they can count them as columns, because they are well arranged in array. You can group them easily, right? So we can see 1, 2, 3, 4, 5, 6 columns, and in each column there are 4 items, 4 cans. So they can do 6 times 4. So either this way or that way you can count. And you can also show it's exactly same amount whether you count this way, so you have 4 times 6 or 6 times 4, it's equal. So you can also teach the commutative property of multiplication there, right? Using rectangular array model. Okay, area model is my favorite. It doesn't have to be your favorite. Okay, area model, I'm gonna show you the virtual manipulatives because I think this is really cool. Before I show you that, this is an area model, the simple one digit by 1 digit. So it's very similar to array model, isn't it? So they can count 3 in each column, and 3 in each column, and there are 4 columns, so 3 times 4 or 4 times 3, or the other way around, right? They can do that. So you can connect that with the previous model. We can extend the digits, using area model, and I'm gonna show you. Okay, so take a look at the website if you are interested in using some virtual manipulatives. I think this is a good website. Sometime soon I'm gonna share you with some virtual manipulatives that I have found useful, but that's just limited because I believe you know more and you can find more. So let's have some time to share that too really soon. Okay, so here's the website that I really like. So I'm gonna extend my area model into like 2 digits, like 24 times 5, for example. So this is 24 times 5, right? And I'm gonna show you, how I use the virtual manipulatives like this as area model. So we know 24 times 5 is like we are counting how many these small squares there are, right? It's kind of tedious. So what we can do is we can break this into smaller parts, like 24 as 20 and 4, for example. Because I know 2 times 5 is 10, then 20 times 5 should be 100. So this is 100. And how about this part? It's 4 times 5, 4 by 5. 4 times 5 is 20. So we know upper part here 20 times 5 plus this part 4 times 5 is exactly same as 24 times 5. That's exactly the same. So instead of doing 24 times 5, we can just do 20 times 5, 100 plus 4 times 5, 20, 120. So that's kind of easy. You can always extend, the digits by 2 digit by 2 digit. Let's do something like that. So you can break this down into 10 digits by 1 digit. So 20 and 5, 19, 20 and 5, 4 and 40 and 5. That's just my option. You can break them into more parts, and you can make this breaking down into different numbers too. This virtual manipulatives does only 2 parts for each number. But if you can draw them on your smartboard or something, you can even break this 40 into 10, 10, 10, 10. And 20 as 10 and 10 as well, and show 100, 100, 100, 100. And you can count them as well. If your students are a little bit advanced, this is also a good thing that you can do with your students, because they know how to calculate 20 times 40 instead of doing 10 times 10 times 10 times 10 times 8 of them. Okay, you know what I mean? Okay, so we can break them down and see 20 times 40 is 800 and 20 times 5 is 100. Here 4 times 40 is 160 and 4 times 5 is 20. So to calculate this, you can add all of them together. This will be related to standard algorithm, because these are actually the partial products. Okay, I will show you that a little bit later too. Okay, so that is the area model. Okay, an area model is also very, very useful because it can also teach the students distributive property easily. So use an area model to find 25 times 15, for example. So we can do 25 times 15. So I have 25 times 15. And you can see 20 times 10 is 200. 20 times 5 is 100. And here 5 times 10 is 50. And this part 5 times 5 is 25. So you can show your students using this area model, we can add these partial products together, right? So this product here is 200 and this product is 100 and this product is 50 and this product is 25. We are just adding all of this together and you get 375, right? How can you connect this to distributive property? 25 times 15 can be broken into 20 and 5, 15 into 10 and 5. You are distributing 20 plus 5 to 10. So 10 is distributed to each of these terms. Then you can distribute 5 to each of these terms, right? That's what I'm writing here. Oops. Oh, I didn't complete that. So you can write here 20 times 10 as 200. 200 is right here, right? 5 times 10, 50. 20 times 5, 100. 5 times 5, 25. So next row, you're going to get exactly same number in this vertical line here. 200 plus 50 plus 100 plus 5, that means 25. And that is equal to 375. So you can see how they are connected, right? So yeah, area model is very useful to teach distributable property. Next model, actually this is the last model before standard algorithm, is lattice model, lattice multiplication model. Maybe some of you are familiar with this model, some of you are not. I am from Pennsylvania, and most of the students in Pennsylvania, when I taught the pro-service teachers there, they only knew lattice model. But when I was teaching here in Nebraska, most of the students didn't know about this model. But after I taught them, they really liked it, and like 60-70% of them wanted to use only this one. So it's kind of funny. I think everyday math, the textbook is using lattice model, but I want you to be limited using only one model. I know I have my preference. I love area model. I like partial product. Maybe you like standard algorithm. Maybe you like lattice model. Maybe you like to just add repeatedly. I don't know, but what I want you to know is there is a connection. Mathematics, any topic in mathematics is not separate. They are all connected. And as a teacher, I want you to show the connection to your students, and I want you to intrigue your students to see the connection and find the connections. Okay? So lattice model, you can write the model in this order. So 37 times 56, starting from here, 37 times 56. It's 2 digit by 2 digits, so you're gonna make a square 2 by 2. Okay, then you're gonna draw the diagonals like that. You're gonna extend the diagonal passing that vertex there. Okay, from top to bottom, top to bottom, top to bottom. And then you're just gonna fill up each of the square. For example, in this square, you're gonna put the number of product of 3 and 5, because this square is where number 3 and 5 are crossing, right? So 3 times 5 is 15, and put tens digit above and ones digit below. When you are multiplying two single digits, it never goes above 2 digits. Like 9 times 9, 9 is the biggest number, it's 81. So it never goes beyond 2 digits. So you just need 2 digit, tens digit and ones digit. How about here? This square, you have a 7 and 5 crossing there. 7 times 5 is 35. So write 3 above, 5 below. This is what I did, right? 35. And this square, 3 times 6, 18. 7 times 6, 42. Okay? Then what you need to do is you're just gonna add in diagonal. So 2, there's nothing but 2, right? So you add them. 2 and 5, 4, 8 all together, it's 17. 4 and 8 is 12, plus 5 is 17. So put only one single digit and carry over the tens digit. So here is the carryover part. You originally had 3, 5, 1, which is 9, but you have another 1 there. So adding them together, you get 10. So ones digit is 0 and tens digit is 1. That's carried over number, but 1 is already there. So add it together and you get 2. So the answer here is 2072. You can also see this in relation with the partial product. I'm not showing it here because I'm gonna leave it to you to compare. Okay, so giving you a small hint. This is a single digit, right? Ones digit, and that's ones digit because it's from 37. So 7 times 6 is 42. So this is ones digit, and that's the tens digit. How about these two? 7 and 5. 7 is ones digit, and that's 50. Actually, it's not 5, right? So 50 times 7 is 350. So this is 350. That 5 is in tens digit. So we know that this is the tens digit, and that becomes a hundredth digit, and that's the thousands digit. I want you to actually compare this with the partial product. Okay, of 37 times 56. Okay, then you will see the connection there. Okay, I have one example here, but I think we can skip it. So you can, actually, I want you to pause this video and practice this, okay? Practice this. So you're gonna do 948 times 827. So you're gonna make 3 by 3 squares there, then put the diagonals from top to bottom to the left. Then what do? You're gonna fill in each square. Lattice model, the good thing about this is you can start from any box. I can start from this, and I know because 8 times 2 is 16, I can put 16. Then you can pick any other square. Well, but you can start from here, you can start from there, so it doesn't actually matter. So you fill up the square by finding the product between these two numbers and these two numbers and these numbers and so on and so on. Then what do? You add them together. In this example, the carryover number is not indicated there, and but I want you to show the carried over number. Then you can just read the number. This is ones digit, tens digit, hundreds digit, thousands digit, 10,000s digit, 100,000s digit. So you start reading the number from here. 783,996. That's gonna be the product of 948 and 827. Okay? Okay, so now we can move on to the standard algorithm of multiplication. So we know the partial product, right? Okay. Okay, so from the example in lattice model, we found that 37 times 56 is equal to 2072. Let's think about the standard algorithm. Before we move on to standard algorithm, we can think about the partial product. Okay, so 37 times 56, we can write it this way. And what we do is distributing 6 to each of these terms, right? So 6 times 7 is 42. And we know 6 times 3 is 18, but this is not 3, it's a 30. So 30 times 6 is 180. So we can write 180 there, right? So we are done with distributing 6 to each of these terms. And now we can distribute 5. But this is not actually 5, it's 50. So when you are doing this with your students, I want you to say 6 times 7, 6 times 30. Don't say that as 3, because it's not 3, it's 30, right? Same for this one. What's 50 times 7? 350. How about, 5 times, this is 50, right? 50 times 30. 50 times 30 is 1,500. So when we add them all together, we get 2, and that's 12, and that's 17 tens. So we have 1 carryover, and we have that as 10. 5, and 5 is 10. So 10,000, and you move that up. 1000, sorry. So we have 2,000, right? So when you compare what we have here, like 42, 180, 350, 1,500, compare that with what you got from lattice model and also from area model, you can see the connections there, okay? And now let's connect that partial product to standard algorithm. So in standard algorithm, what we do is this. 6 times 7 is 42, and we put 4 here because it's 4 tens, right? Then we do 6 times 3. 6 times 3 is what? 18, and we put 18 here, but since there's 4 added to it, we have 22. But that's actually 22 tens, right? And then there's nothing, so you write 222 there. And then what we do here is we empty this place and start from this digit. Some school teachers sadly don't explain it why. But I want you to explain why. Why do we start from this, not this? Because we are multiplying this number by tens digit. So there is no ones digit, right? So when you multiply 50 by 7, that's 350. So that's 350. So that 3 goes up here. That's carried over number. 5 times 3, actually 50 times 3 is what? 1500. But since we have 300 there, it becomes 800. And then we can add them together. We have 2, 7, and 2 there. So exactly the same number. Can you connect these two? What we got here is from 37 times 6, isn't it? 37 times 6. 30 times 7, 6 are these two numbers together. So when you add these two together, you get 222, right? And then we multiplied 50 by 37 and we got 1850. Same here. When we multiplied 50 by 7, we got 350. And when we multiplied 50 by 30, we got 1500. So when we multiplied 37 by 5, that's exactly same as this number, right? So when you add them together, the answer should be the same, 2072. So you can explain why the standard algorithm works using the partial product. That's one way. You can also, connect this with area model too, or lattice model as well. And I want you to find the connections as the homework, okay? Okay. Also, if the students use only the standard algorithm, I think they can make more mistakes easily. So why do we have to push them use only standard algorithm? You don't have to, right? If they prefer to use partial product because they can, reduce the error, I would say, yeah, use that because that makes more sense to you. Why not doing that? I don't think it harms, right? Okay. Now I want you to consider students invented strategies. You know how much I love to see students invented strategies and to try to understand what their thinking is, right? Okay, so I will just show you some students' strategies and give you a few minutes to think about what it is about before I explain my understanding, okay? So how about you pause the video and think about each of the students' strategy, okay? So this one, I put that as complete number strategies, including doubling. So what I noticed is, to multiply 63 times 5, I think this student knew it's repeated addition, and he wanted to use the repeated addition strategies. And also this student knew 63 plus 63 is 126, and rather than adding 63 to 126, he wanted to use the doubling. So 63 times 5 is the same as 63 plus 63 plus 63 plus 63 plus 63. You can keep adding that, right? Or you can also do the doubling here. So 63 plus 63 is 126. Then sum of these two is also 126, right? So you can just add 63 to it, and that's 189, and you're adding that to 126. So that's 315. So either keep adding 63 5 times, 1, 2, 3, 4, 5, or using some addition strategy like doubling. You can check your own answer, or you can just calculate the multiplication. But it seems like this student you use the knowledge about the multiplication as repeated addition, right? Okay. Let's take a look at this strategy. I named it as partitioning strategies because this student partitioned the numbers. For example, here 27 times 4, this student partitioned 27 as 20 and 7. So 20 and 7 and used the distributive property. Maybe the student didn't know about distributive property that he's using, but he did. So he did 20 times 4 or 4 times 20, and he did 4 times 7. Wow, maybe this student knew that the commutative property, knowing that 4 times 20 is the same as 20 times 4. So he found 80 and 28 as each of the partial product and added it. Similar to this strategy, this student partitioned 268. I think Common Core standards, in practice standards, they're talking about decomposition, right? So decompose 268 as 200 plus 60 plus 8 and distributed each of them to 7. So 200 times 7 or 7 times 200, 7 times 60, 7 times 8 and added them together, right? Let's take a look at this one, partitioning the multiplier. So this student, this is really interesting. So instead of partitioning 46, the multiplicand, as 40 and 6, I'm sorry that I use the multiplicand, but because this textbook is from Van de Waal, saying multiplier, I'm using multiplicand, but we prefer to use factor and factor. But in this case, this is multiplier and this is multiplicand because it's multiplied by 3 and 3 is multiplying to 46. We call that multiplier, but just use factor for your students, okay? Anyways, instead of partitioning this number, this student partitioned 3 as 2 and 1. So if you do 46 times 1, you get 46. But when you have 46 times 2, that's doubling of it. So 92. So 3 is 1 plus 2, so times 1 and times 2, right? So 46 times 1 is 46, 46 times 2 is 92. Then you can add them together, which is 138. Pretty cool. Okay, this one by tens and ones. So instead of just partitioning 27 as 20 and 7, this student broke more from 20. So breaking 20 as 10 and 10 and 7. So 10 times 4 is 40, again 40, and 7 times 4. That's exactly the same as 27 times 4. And then you add them together, right? And different partitioning can be, relating the number to each number, like money. So maybe the student thought 27 is very close to 25, and I know when I have 1 quarter it's 25 cents, and when I have 4 quarters that's 100 cents. So 25 times 4 is easy for me, and I know 25 times 8 is 200 cents. So changing 27 to 25. Then what is remaining here? 2, right? So 2 times 8 is 16. So this student did 25 times 8 is 200, knowing that 25 times 4 is 100, right? And then added 2 times 8 equals 16 to that. So that is really cool strategy, all about partitioning or decomposing. Compensation strategies for multiplication. It's pretty cool too. So this is kind of similar to, this one. So take a look. So when this student did 27 times 4, he changed it 27 to 30 by adding 3 to 27, right? So instead of multiplying 27 by 4, he did 30 times 4 and got 120. But he knew that he added 3 to it, so he needs to subtract 3, right? So he subtracted 12 right here and got 108 by taking away 12 from 120. Let's take a look at this. 250 times 5. Oh, it's nice that this person explained. I can split 250 in half, which is 125, right? And multiply that by 10. Wow, that's pretty cool, isn't it? Because if you split this into half, that's divided by 2. But since you divided by 2, you actually need to multiply that by 2 to compensate to make 250 itself. Because divided by 2 is multiplied by 1 half. If you multiply 2 to 1 half, it's exactly same as 1. And times 1 is always 1 itself, right? So 250 divided by 2 times 2, it's just times 1. So you still get the same number. Nothing has been changed. That's what this student was thinking. So divide this by 2, then multiply this by 2. Then it's not going to change any, the product there. So 250 divided by 2, which is 125, and multiply that by 2, but you have multiplication the total by 5. So 2 times 5 is 10 and got 1,250. Really cool. How about this one? 17 times 20, 70. 17 is kind of not fun number, not easy number, so this student changed that to 20. So instead of doing 17 times 70, he or she did 20 times 70. But you need to keep thinking about, because I added by 3, I need to take that away. But since it's multiplied by 70, later I need to take away 3 times 70, right? Keeping that in mind, the student did 20 times 70 is 1400, and then take away 3 times 70 and got 1,190. I love this idea, but also I really love this student used arrow instead of using equal sign, because we noticed that a lot of students misuse equal sign. When it is not equal to each other, they use it. But this student didn't put equal sign because it's not equal. He just knew that 20 times 70 is 1,400. These two are equal, but this whole thing and that whole thing on the left hand side and right hand side, it's not equal. So I'm so glad the student did not use equal sign there. Okay? All right, so yeah, what do you think so far? The students inventing strategies, I think it's pretty cool. And they can always think beyond what we are teaching in classroom, don't you think? Let's take a look at this one. The problem was this. There were 35 dog sleds. Each sled was pulled by 12 dogs. How many dogs were there in all? So the student here added 35 12 times, right? Could do 35 12 times, and you add that up and it equal to 420. So 35 times 12 is 420. So yeah, basically the student did just, added them together. Brianna did. Brianna just added all of these numbers together because 5, adding 5 12 times is kind of easy, 60, and then add them together. So using the knowledge of repeated addition, he could do that. She could do that. How about Kenneth? 35 times 12. The student, Kenneth, knew that he can use multiplication instead of doing repeated addition. So when solving this multiplication, use the partitioning there, right? So 30, instead of 30, he partitioned the 30 into 3 tens, and then there's 5. So 10 times 12, 10 times 12, 10 times 12, 5 times 12, and added them all together, right? How about Nick? Nick did 35 times 12 is 30 times 10. So 30 times 10 and 30 times 2 using distributive property, and then 5 times 10 and 5 times 2. 5 times 10 and 5 times 2. And then add them all together. Use the, distributive property or partial product, right? Okay, so that was pretty cool. And let's take a look at this standard algorithm that student used. So here, 4 times 6 is 24, and 80 times 6 is 480, and add them together, right? 4 and 10 tens, so there are 5 hundreds, right? That's same as this, so this is a partial product. That's same as this standard algorithm. 4 times 6 is 24, and 8 times 6 is 48, but since it's a tens place, we're just gonna add that by 2 tens. So you can see the connections there, and you can do the same thing for any digits there too. One thing I want to mention here is the digit, the place values. So one recommendation that you can do is think about use your notebook. Usually the notebooks have horizontal lines like that, right? You can flip it over 90 degrees. Then you're gonna have these vertical lines. So you can encourage your students solve any addition, subtraction, multiplication, or division using their notebook sideways, so they don't mess up. They don't mess up with the digits or place values. So I strongly encourage you to help your students when they are, initially learning about the standard algorithm, partial product, or even addition, subtraction, multiplication, division, all of these operations. They can pay extra attention when there are lines like that. So if they use their notebooks sideways, they can have those lines that divides each of the digits, each of the place value they can pay attention to. So I think that's pretty cool to do that. What do you think? Okay. Yeah, here's another thing that I want to mention. So we talked about area model. This is very, very similar to area model. So it is the area model, but using base 10 blocks. So 36 times 47 can be written as 30 tens. We need to change that. 3 tens, right? So 3 tens and 6 ones, 4 tens and 7 ones, right? So here's 3 tens and 6 ones, 4 tens and 7 ones. So you can just count how many there are. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You have 12 100s. These flats are 100s, right? And you can take a look at this part. It's 6 times 40, which is 240, and so on and so on. So you can see the connections there. We already talked about that earlier, right? And you can connect that to standard algorithm. Okay, that's all for this week. So we talked a lot about the different models to solve multiplication, and we looked at the connections there. So I want you to deeply think about the reasoning for multiplication. And also we looked at the students invented strategies to solve multiplication, and we found they are really, really cool, right? So thinking about that, the homeworks are these. The first one you need to do is this. We have talked about several strategies to solve a multiplication problem. Choose at least 3 strategies and discuss how these 3 strategies are connected. If you do more than 3, I think it's gonna be really cool. And I want you to show with actual example of 253 times 84. So if you want to show, for example, the partial product, I want you to use actual numbers to compare, okay, and show the connections there. You can take a picture or you can type in whichever you want to do it and post it, okay? And the second part is, I want you to invent your own strategy to solve the same problem, 253 times 84. Or you can ask your student to multiply 253 times 84 on their own way, so they can invent their own strategy. So if you ask your like fourth, fifth, or above grade students, they already know standard algorithm, so it's not gonna be fun. They may use the standard algorithm. That's not what we want, right? So maybe think about very young students like second grade or early third grade, who doesn't know about standard algorithm. Then you can pour out a lot of fun stuff there. Okay, so either way, you invent your own strategy or you find a good invented strategy from your student or your colleagues, teachers, student, or whoever, young student. That is different from what we have talked about in today's lesson. So I want to see something new there, okay, and share that strategy and explain what's going on there. Okay, again, I want you to read other students' posts and respond to them. Okay, all right, have a great week, guys, and I will see you next week.